SRM and the 5P check. SRM is about how to gather information, analyze it, and make decisions. Learning how to identify problems, analyze the information, and make informed and timely decisions is not as straightforward as the training involved in learning specific maneuvers. Learning how to judge a situation and how to think in an endless variety of situations encountered while flying out in the real world is more difficult. There is no one right answer in ADM. Rather, each pilot is expected to analyze each situation in light of experience level, personal minimums, and current physical and mental readiness level, and make his or her own decision. SRM sounds good on paper, but it requires a way for pilots to understand and use it in their daily flights. One practical application is called the 5 Ps. The 5 Ps consist of the plan, the plane, the pilot, the passengers, and the programming. Each of these areas consists of a set of challenges and opportunities that face a single pilot, and each can substantially increase or decrease the risk of successfully completing the flight based on the pilot's ability to make informed and timely decisions. The 5 Ps are used to evaluate the pilot's current situation at key decision points during the flight, or when an emergency arises. These decision points include pre-flight, pre-takeoff, hourly or at the midpoint of the flight, pre-descent, and just prior to the final approach fix, or for visual flight rules VFR operations, just prior to entering the traffic pattern. The 5 Ps are based on the idea that the pilots have essentially 5 variables that impact his or her environment, and that can cause the pilot to make a single critical decision or several less critical decisions that, when added together, can create a critical outcome. These variables are the plan, the plane, the pilot, the passengers, and the programming. The 5P concept relies on the pilot to adopt a scheduled review of the critical variables at points in the flight where decisions are most likely to be effective. For instance, the easiest point to cancel a flight due to bad weather is before the pilot and passengers walk out the door and load the aircraft. So the first decision point is pre-flight in the flight planning room, where all the information is readily available to make a sound decision, and where communication and fixed base operator FBO services are readily available to make alternate travel plans. The second easiest point in the flight to make a critical safety decision is just prior to takeoff. Few pilots have ever had to make an emergency takeoff. While the point of the 5P check is to help the pilot fly, the correct application of the 5P before takeoff is to assist in making a reasoned go-no-go decision based on all the information available. That decision will usually be to go, with certain restrictions and changes, but may also be a no-go. The key point is that these 2 points in the process of flying are critical go-no-go points on each and every flight. The third place to review the 5 Ps is at the midpoint of the flight. Often, pilots may wait until the Automated Terminal Information Service, ATIS, is in range to check weather. Yet at this point in the flight, many good options have already passed behind the aircraft and pilot. Additionally, fatigue and low-altitude hypoxia serve to rob the pilot of much of his or her energy by the end of a long and tiring flight day. This leads to a transition from a decision-making mode to an acceptance mode on the part of the pilot. If the flight is longer than 2 hours, the 5P check should be conducted hourly. The last 2 decision points are just prior to descent into the terminal area and just prior to the final approach fix, or if VFR, just prior to entering the traffic pattern, as preparations for landing commence. Most pilots execute approaches with the expectation that they will land out of the approach every time. A healthier approach requires the pilot to assume that changing conditions, the 5 Ps again, will cause the pilot to divert or execute the missed approach on every approach. This keeps the pilot alert to all manner of conditions that may increase risk and threaten the safe conduct of the flight. Diverting from cruise altitude saves fuel, allows unhurried use of the autopilot, and is less reactive in nature. Diverting from the final approach fix, while more difficult, still allows the pilot to plan and coordinate better rather than executing a futile missed approach. Let's look at a detailed discussion of each of the 5 Ps. The plan. The plan can also be called the mission or the task. It contains the basic elements of cross-country planning: weather, route, fuel, publications, currency, etc. The plan should be reviewed and updated several times during the course of the flight. A delayed takeoff due to maintenance, fast-moving weather, and a short-notice TFR may all radically alter the plan. The plan is not only about the flight plan, but also all the events that surround the flight and allow the pilot to accomplish the mission. The plan is always being updated and modified and is especially responsive to changes in the other 4 remaining Ps. If for no other reason, the 5P check reminds the pilot that the day's flight plan is real life and subject to change at any time. Obviously, weather is a huge part of any plan. The addition of data link weather information gives the advanced avionics pilot a real advantage in inclement weather, but only if the pilot is trained to retrieve and evaluate the weather in real time without sacrificing situational awareness. And of course, weather information should drive a decision, even if that decision is to continue on the current plan. Pilots of aircraft without data link weather should get updated weather in flight through a flight service station, FSS, and/or Flight Watch. The plane. Both the plan and the plane are fairly familiar to most pilots. The plane consists of the usual array of mechanical and cosmetic issues that every aircraft pilot, owner, or operator can identify. With the advent of advanced avionics, the plane has expanded to include database currency, automation status, and emergency backup systems that were unknown a few years ago. Much has been written about single-pilot IFR flight, both with and without an autopilot. While this is a personal decision, it is just that, a decision. Low IFR in a non-autopilot-equipped aircraft may depend on several of the other Ps to be discussed. Pilot proficiency, currency, and fatigue are among them. The pilot. Flying, especially when used for business transportation, can expose the pilot to high-altitude flying, long distance and endurance, and more challenging weather. An advanced avionics aircraft, simply due to their advanced capabilities, can expose a pilot to even more of these stresses. The traditional I'm safe checklist, see page 17-6, is a good start. The combination of late night, pilot fatigue, and the effects of sustained flight above 5,000 feet may cause pilots to become less discerning, less critical of information, less decisive, and more compliant and accepting. Just as the most critical portion of the flight approaches, for instance a night instrument approach in the weather after a 4-hour flight, the pilot's guard is down the most. The 5P process helps a pilot recognize the physiological situation at the end of the flight before takeoff and continues to update personal conditions as the flight progresses. Once risks are identified, the pilot is in an infinitely better place to make alternate plans that lessen the effects of these factors and provide a safer solution. The passengers. One of the key differences between CRM and SRM is the way passengers interact with the pilot. The pilot of a highly capable single-engine aircraft has entered into a very personal relationship with the passengers. In fact, the pilot and passengers sit within an arm's reach all of the time. The desire of the passengers to make airline connections or important business meetings easily enters into this pilot's decision-making loop. Done in a healthy and open way, this can be a positive factor. Consider a flight to Dulles Airport, and the passengers, both close friends and business partners, need to get to Washington, D.C. for an important meeting. The weather is VFR all the way to Southern Virginia, then turns to low IFR as the pilot approaches Dulles. A pilot employing the 5P approach might consider reserving a rental car at an airport in northern North Carolina or Southern Virginia to coincide with a refueling stop. Thus, the passengers have a way to get to Washington, and the pilot has an out to avoid being pressured into continuing the flight if the conditions do not improve. Passengers can also be pilots. If no one is designated as pilot in command, PIC, and unplanned circumstances arise, the decision-making styles of several self-confident pilots may come into conflict. Pilots also need to understand that non-pilots may not understand the level of risk involved in the flight. There is an element of risk in every flight. That is why SRM calls it risk management, not risk elimination. While a pilot may feel comfortable with the risk present in a night IFR flight, the passengers may not. A pilot employing SRM should ensure the passengers are involved in the decision-making and given tasks and duties to keep them busy and involved. If, upon a factual description of the risks present, the passengers decide to buy an airline ticket or rent a car, then a good decision has generally been made. This discussion also allows the pilot to move past what he or she thinks the passengers want to do and find out what they actually want to do. This removes self-induced pressure from the pilot. The programming. The advanced avionics aircraft adds an entirely new dimension to the way GA aircraft are flown. The electronic instrument displays, GPS, and autopilot reduce pilot workload and increase pilot situational awareness. While programming and operation of these devices are fairly simple and straightforward, unlike the analog instruments they replace, they tend to capture the pilot's attention and hold it for longer periods of time. To avoid this phenomenon, the pilot should plan in advance when and where the programming for approaches, route changes, and airport information gathering should be accomplished, as well as times it should not. Pilot familiarity with the equipment, the route, the local air traffic control environment, and personal capabilities vis-à-vis the automation should drive when, where, and how the automation is programmed and used. The pilot should also consider what his or her capabilities are in response to last-minute changes of the approach and the reprogramming required, and ability to make large-scale changes, a reroute for instance, while hand-flying the aircraft. Since formats are not standardized, simply moving from one manufacturer's equipment to another should give the pilot pause and require more conservative planning and decisions. The SRM process is simple. At least 5 times before and during the flight, the pilot should review and consider the plan, the plane, the pilot, the passengers, and the programming, and make the appropriate decision required by the current situation. It is often said that failure to make a decision is a decision. Under SRM and the 5 Ps, even the decision to make no changes to the current plan is made through a careful consideration of all the risk factors present. The Ooda Loop. Colonel John Boyd, United States Air Force's retired, coined the term and developed the concept of the Ooda Loop: observation, orientation, decision, action. The ideas, words, and phrases contained in Boyd's briefings have penetrated not only the United States military services, but the business community and worldwide academia. The Ooda Loop is now used as a standard description of decision-making cycles. The loop is an interlaced decision model which provides immediate feedback throughout the decision-making process. For SRM purposes, an abbreviated version of the concept shown here provides an easily understood tool for the pilot. The first node of the loop, observe, reflects the need for situational awareness. A pilot must be aware of those things around him or her that may impact the flight. Continuous monitoring of aircraft controls, weather, etc. provides a constant reference point by which the pilot knows his or her starting point on the loop, which permits the ability to immediately move to the next step. Orient, the second node of the loop, focuses the pilot's attention on one or more discrepancies in the flight. For example, there is a low oil pressure reading. The pilot is aware of this deviation and considers available options in view of potential hazards to continued flight. The pilot then moves to the third node, decide, in which he or she makes a positive determination about a specific effect. That decision is made based on experience and knowledge of potential results, and to take that particular action will produce the desired result. The pilot then acts on that decision, making a physical input to cause the aircraft to react in the desired fashion. Once the loop has been completed, the pilot is once again in the observe position. The assessment of the resulting action is added to the previously perceived aspects of the flight to further define the flight's progress. The advantage of the Ooda Loop model is that it may be cumulative, as well as having the potential of allowing for multiple progressions to occur at any given point in the flight. The DECIDE model. Using the acronym DECIDE, the six-step process DECIDE model is another continuous loop process that provides the pilot with a logical way of making decisions. DECIDE means to detect, estimate, choose a course of action, identify solutions, do the necessary actions, and evaluate the effects of the actions. First, consider a recent accident involving a Piper Apache, PA-23. The aircraft was substantially damaged during impact with terrain at a local airport in Alabama. The Certificated Airline Transport Pilot, ATP, received minor injuries, and the Certificated Private Pilot was not injured. The private pilot was receiving a check ride from the ATP, who was also a designated examiner, for a commercial pilot certificate with a multi-engine rating. After performing air work at altitude, they returned to the airport, and the private pilot performed a single-engine approach to a full-stop landing. He then taxied back for takeoff, performed a short-field takeoff, and then joined the traffic pattern to return for another landing. During the approach for the second landing, the ATP simulated a right engine failure by reducing power on the right engine to zero thrust. This caused the aircraft to yaw right. The procedure to identify the failed engine is a two-step process. First, bring power to maximum controllable on both engines. Because the left engine is the only engine delivering thrust, the yaw increases to the right, which necessitates application of additional left rudder. The failed engine is the side that requires no rudder pressure, in this case the right engine. Second, having identified the failed right engine, the procedure is to feather the right engine and adjust power to maintain descent angle to a landing. However, in this case, the pilot feathered the left engine because he assumed the engine failure was a left engine failure. During twin-engine training, the left engine out is emphasized more than the right engine because the left engine on most light twins is the critical engine. This is due to multi-engine airplanes being subject to P factor, as are single-engine airplanes. The descending propeller blade of each engine will produce greater thrust than the ascending blade when the airplane is operated under power and at positive angles of attack. The descending propeller blade of the right engine is also a greater distance from the center of gravity and therefore has a longer moment arm than the descending propeller blade of the left engine. As a result, failure of the left engine will result in the most asymmetrical thrust, adverse yaw, because the right engine will be providing the remaining thrust. Many twins are designed with a counter-rotating right engine. With this design, the degree of asymmetrical thrust is the same with either engine inoperative. Neither engine is more critical than the other. Since the pilot never executed the first step of identifying which engine failed, he feathered the left engine and set the right engine at zero thrust. This essentially restricted the aircraft to a controlled glide. Upon realizing that he was not going to make the runway, the pilot increased power to both engines, causing an enormous yaw to the left. The left propeller was feathered, whereupon the aircraft started to turn left. In desperation, the instructor closed both throttles, and the aircraft hit the ground and was substantially damaged. This case is interesting because it highlights two particular issues. First, taking action without forethought can be just as dangerous as taking no action at all. In this case, the pilot's actions were incorrect, yet there was sufficient time to take the necessary steps to analyze the simulated emergency. The second and more subtle issue is that decisions made under pressure are sometimes executed based on limited experience, and the actions taken may be incorrect, incomplete, or insufficient to handle the situation. Detect the problem. Problem detection is the first step in the decision-making process. It begins with recognizing a change occurred or an expected change did not occur. A problem is perceived first by the senses, and then it is distinguished through insight and experience. These same abilities, as well as an objective analysis of all available information, are used to determine the nature and severity of the problem. One critical error made during the decision-making process is incorrectly detecting the problem. In the example above, the change that occurred was a yaw. Estimate the need to react. In the engine out example, the aircraft yawed right. The pilot was on final approach, and the problem warranted a prompt solution. In many cases, overreaction and fixation excludes a safe outcome. For example, what if the cabin door of a Mooney suddenly opened in flight while the aircraft climbed through 1,500 feet on a clear sunny day? The sudden opening would be alarming, but the perceived hazard the open door presents is quickly and effectively assessed as minor. In fact, the door's opening would not impact safe flight and can almost be disregarded. Most likely, a pilot would return to the airport to secure the door after landing. The pilot flying on a clear day faced with this minor problem may rank the open cabin door as a low risk. What about the pilot on an IFR climb-out in IMC conditions with light intermittent turbulence in rain, who is receiving an amended clearance from Air Traffic Control, ATC? The open cabin door now becomes a higher risk factor. The problem has not changed, but the perception of risk a pilot assigns it changes because of the multitude of ongoing tasks and the environment. Experience, discipline, awareness, and knowledge will influence how a pilot ranks a problem. Choose a course of action. After the problem has been identified and its impact estimated, the pilot must determine the desirable outcome and choose a course of action. In the case of the multi-engine pilot given the simulated failed engine, the desired objective is to safely land the airplane. Identify solutions. The pilot formulates a plan that will take him or her to the objective. Sometimes there may be only one course of action available. In the case of the engine failure, already at 500 feet or below, the pilot solves the problem by identifying one or more solutions that lead to a successful outcome. It is important for the pilot not to become fixated on the process to the exclusion of making a decision. Do the necessary actions. Once pathways to resolution are identified, the pilot selects the most suitable one for the situation. The multi-engine pilot, given the simulated failed engine, must now safely land the aircraft. Evaluate the effect of the action. Finally, after implementing a solution, evaluate the decision to see if it was correct. If the action taken does not provide the desired results, the process may have to be repeated. Decision-making in a dynamic environment. The common approach to decision-making has been through the use of analytical models such as 5P, 3P, Ooda, and DECIDE. Good decisions result when pilots gather all available information, review it, analyze the options, rate the options, select a course of action, and evaluate that course of action for correctness. In some situations, there isn't always time to make decisions based on analytical decision-making skills. A good example is a quarterback whose actions are based upon a highly fluid and changing situation. He intends to execute a plan, but new circumstances dictate decision-making on the fly. This type of decision-making is called automatic decision-making or naturalized decision-making, shown on the right half of the figure. In an emergency situation, a pilot might not survive if he or she rigorously applied analytical models to every decision made. There is not enough time to go through all the options. But under these circumstances, does he or she find the best possible solution to every problem? For the past several decades, research into how people actually make decisions has revealed that when pressed for time, experts faced with a task loaded with uncertainty first assess whether the situation strikes them as familiar. Rather than comparing the pros and cons of different approaches, they quickly imagine how one or a few possible courses of action in such situations will play out. Experts take the first workable option they can find. While it may not be the best of all possible choices, it often yields remarkably good results. The terms naturalistic and automatic decision-making have been coined to describe this type of decision-making. The ability to make automatic decisions holds true for a range of experts from firefighters to chess players. It appears the expert's ability hinges on the recognition of patterns and consistencies that clarify options in complex situations. Experts appear to make provisional sense of a situation, without actually reaching a decision, by launching experience-based actions that in turn trigger creative revisions. This is a reflexive type of decision-making anchored in training and experience, and is most often used in times of emergency when there is no time to practice analytical decision-making. Naturalistic or automatic decision-making improves with training and experience, and a pilot will find himself or herself using a combination of decision-making tools that correlate with individual experience and training. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.